Good day, everyone. My name is Lori Berger. I'm the Chief Marketing Officer at CBT Technology. Thank you for attending XTech's Keys to Front Panel Design webinar today, sponsored by CBT Technology, the global supplier of XTech and EEE products for commercial and ruggedized applications. Front panel design is often an afterthought in the design of a board or blade, with most of the focus being on the electronics and software. But the front panel is a key mechanical component which ties the elements of the chassis together. Today, we will explore some of the critical design elements to help you avoid those obstacles to success in a front panel solution. And to help identify those keys to a successful design, we have with us Matt Travers. Matt is a senior application engineer with extensive experience in front panel design from a customer perspective, as well as a strong background in the applicable mechanical standards. So to open the door on key design elements, I will turn the webinar over to Matt.
Okay, again, welcome everybody. Glad you're able to make it. We're going to try to go through some of these elements that Lori had talked about and look for ways that we can effectively assist you or assist anyone to design the front panels. Of course, before we get into the designing of the front panel specifically, there are a couple of decisions that have to be made, and the first one really being what the overall direction is going to be regarding a system, whether it's going to be a standards-based system that is an open architecture, as you see over here on the left, and then on the right we have examples of a completely custom system. Really the difference between the two is that the standards are pretty well set. The specifications have been written, the front panel form factors, the chassis interface, the way that they connect with the back planes. There's a wide range of options out there. All of those things will have been set and established by a standard. So it's really easy to do. A lot of people feel that that's the way to go because the work has pretty much been done as far as an engineering standpoint. It's just a matter of sort of plugging into that existing standard. Or again, if you're actually going to provide a product that sells right into a standard, well, that's obviously important too, to understand how it all works together. If you have a custom system, none of that really matters. You're doing your own thing, and they're pretty much wide open regarding the connectors used, the backplane interfaces, and how the front panels work, and the whole system itself is a little bit more open. So understanding either one of those is an important thing. The message here from the standpoint of CBT is that we are executive members of PICMIG. We're also members of VITA. We have extensive knowledge about advanced TCA, MCs, micro TCAs, those products, and a lot of VPX stuff, which is a newer one kind of coming online. So we have a lot of products and knowledge on that. And then again, from the standpoint of the custom system, well, a huge percentage of the business that we do actually is based on the custom work. So we have some ideas about that. And we are pretty much going to focus on that through the course of this particular presentation. So it is important to understand the details of the chassis design, and again, whether it is a custom or whether it is an open system itself. And some of those things that are very important as you take a look at the front panel to understand, maybe even first, or definitely first, is the overall design of the chassis and some of the overall issues that you can run into, especially when it comes to tolerancing. You know, a lot of various components that all have to work and fit and plug together here. And of course, there's a lot of tolerances and tolerancing considerations that have to be kept in mind as you're looking at that. So it's important for us to really understand how those blades or how the front panels really work in the functioning of the whole system. Some of these necessary tolerance considerations, as I said here, the depth of the blade as related to the depth of the chassis itself is an important thing to make sure you're getting proper connectivity with the backplane connectors, as well as a proper mate and fit with the front panel itself. Of course, the way the ejector works and actuates, making sure that you have enough leverage that you can effectively insert and extract these connectors from the backplane, very important thing. And then from a side-to-side standpoint, you have the concern of the pitch or the area, the home that each one of those blades needs to fit in. Each one of those faceplates needs to fit in. And then the relationship of faceplate to faceplate to faceplate all the way down. And of course that relates very closely to not just the backplane connectors, but the position of the card guides themselves. And then as we'll talk a little bit about as we go forward, the importance to maintain a certain gap between each one of those front panels to allow the EMI to work properly and have the right have the right distance so that you have shielding effectiveness there as well. So we'll focus on 5 different keys to success for the front panel, and those 5 keys are, first of all, choosing the proper front panel manufacturing process and material. So we've got some options there we'll talk about first. Second, actually we'll spend more time on that number 1, I think, than the other ones, but that's going to be a pretty key thing. Number 2 is the right ejector and what some of the options and availability for ejectors would be there. The third one is choosing the right EMI gasket. We'll look at some of those options. And then for the fasteners, and then finally we'll finish up with the finishing options or labeling options and different ways to make the overall front panel sort of look nice. That's an important thing, obviously, too. So we take a look at what we have for options, really. We'll talk about sheet metal when we talk about the materials or the process itself. We have aluminum extrusions, which we'll delve into, and then finally we will talk about some options with die-casted parts for front panels. So to start with, again, sheet metal. So sheet metal is a process that's been around for a long time and pretty well tried and true. A lot of engineers and people that we work with are very familiar with sheet metal, whether it's the front panel or whether it's some ancillary components. Either way, CBT has a wide range of technology to be able to utilize for the manufacture of sheet metal front panels as well. So some of the positive things about sheet metal, that there are some different options with the actual material itself. If you need the product to be a little lighter, well, aluminum would be a good option. Aluminum can be punched and formed into shapes and into the actual form needed. So that's a good thing. Stainless steel and cold rolled steel as well. So if something needed to be a little bit more rigid, well, then you can choose some different materials, all pretty much being able to be used on the same equipment or manufactured from the same equipment, that equipment being either turret punching or laser processing. Either one of those processes can be used to produce the material. And the nice part about that is usually the tooling is pretty well established, which means there's no additional charges. And then usually if you went with a laser cutting, well, then you're really not dealing with any tooling charges at all, because it's pretty much a computerized laser that produces that shape. And then after that, those sheets are fabricated or formed into the various profiles that are required. Shown down here in the lower left is just some of the features and how those features can be developed. And clearly you can see there's forming that needs to take place. And most of the features required for an effective front panel can be acquired with the sheet metal process. So there's obviously no issues there. And some of these images sort of show some of those features and how they're bent in to that. So another interesting feature is the component covers. We've seen a lot of use for component covers, especially if we go back to the standards discussion in the advanced TCA world. Having those secondary side covers to protect componentry is important. So instead of having a second piece, that's can be included as an integral part of the front panel itself. Sometimes that's required, sometimes that's not required or not even needed, but if that is the case, it's all sort of built in. So it can be a cost-effective way to go. That's how we look at the sheet metal technology. When we talk about that front panel itself, the issue usually is not the length of the front panel. The issue is not the feature to feature, as we would consider, or the I/O. So if you have connectors in the front, the dimensions and tolerances from one connector to another can be held very tightly. Same with all machining processes, so there's no issue with that there. But some of the problems that we have to concern ourselves with occasionally would be the formed tolerances. So as you form a sheet metal part from a flat piece of sheet stock, each one of those forms has a tolerance associated with it. So the more forms you have, the more of an opportunity for that tolerance to grow, as you see here. Along the front face, to hold plus or minus 10 thousandths or even better, not too much of a concern, really. That's something that's easy to do. But as you get toward the back side of the front panel, now you're looking at having to control a dimension that includes multiple forms to derive that dimension, and therefore the tolerances do sort of accumulate to some extent. All these things can be sort of negotiated and worked with. This is a general rule of thumb, not meant to be anything set in stone, but one of those things to be concerned about. So if we take a look at some of the pros and the cons, we sort of discussed some of this already, but it's a cost-effective way to go. Very low tooling costs, actually, if any, in a lot of cases. You can get into some very small quantities of sheet metal parts without really having to worry too much about the tooling costs being high, if any at all. And then, of course, having multiple options for different types of materials can be an important thing too. So that's a good thing. Some of the cons, and I put down aesthetics here. It's really sort of subjective, isn't it? I look at the aesthetics being not quite as much as some of the, or as nice as some of the other technologies that are out there, just because of the forming operations. It does look like a formed part. It doesn't look as crisp and clean. But again, that's in the eye of the beholder. Some might say that they either like that look, they want that look, or in some cases, it doesn't really matter, the aesthetics, as much. So that might not even be a con at all in some cases. And then, as we had discussed too, some of those feature tolerances can at times sort of grow a little bit there too. So just a few things to keep in mind as you're looking at deciding whether to use that technology. We switch on to the second one here, which is aluminum extrusions, something that's a little near and dear to us only because we do have our own extrusion press over here in Randolph, so we have a lot of experience doing that. Most of our sheet metal technologies and capabilities, although we do have it here in Randolph, most of that is taken care of at our China facilities. But at any rate, aluminum extrusions offer some various features. As you can see, a lot of the things that you can get from a sheet metal part is the same thing with an extruded part, although an extruded part being a process where hot material is simply forced through a die. Whatever you cut into the shape of that die is what provides that shape. It does allow a few more options for some features. Some things that you cannot get with sheet metal, for instance, would be a feature like this retention feature for the EMI gasketing. So having a feature like this, as is shown in a few of these images, that's something that is very, very unique to an extrusion. Also having, as we see up here, a real square or tight corners, sharp edges, a recess for the overlay in the front of the part if an overlay is being used. All those things can be provided pretty easily with an aluminum extrusion. And some of the offsets and stuff, instead of being bent, again, they're just formed right into the extrusion die itself. So those are some of the features that are available. Oh, and a big one is a differing wall thickness. Whereas when you have with a sheet metal part, you're pretty much locked into one thickness of material all the way through because it's a sheet that you're punching. With aluminum extrusion, we can offer a different wall thickness. Very important in a case where you have possibly some I/O shielding requirements that might require a little bit more thickness in the front of the panel. Again, with an extrusion, that's something that can be offered and built right in. A little bit thicker here than you would have in the sidewalls for those kinds of technology. So a couple of good features that extrusions give to you. As far as tolerances are concerned, the discussion's a little more complex than a sheet metal one, only because of the process of the extrusion. It does require some more considerations. This is one of those things that we find that the earlier we're involved in that, the better off, because we can really work with you to try and determine the best, or what the tolerances really, what tolerances you need and the best way for us to achieve that. So I think in general, the best way to look at this is that as the cross-section increases in either size or complexity, then the tolerances also sort of follow that. So it's not one set of numbers. For instance, with the machining process, we're all used to, we have plus or minus 5 thousandths across the board and we're covered. Well, that's fine because you can control that with machining. But you'll notice here, for instance, with dimension A as an example, as the actual range of the dimension itself grows, you'll see the tolerance actually grows along with it. And that does obviously become an issue too toward the back, again, as we have plus or minus 1 degree angular tolerances, which are more greatly affected, in the back of the front panel. That's not unlike what we saw with the sheet metal, really, in that case. So without getting into too much detail here, the bottom line is that we want to just ensure that people are aware that there are extrusion tolerances that are larger than machining tolerances, and therefore something that needs to be considered, and we would love to be able to help. So again, the earlier we're involved in that, the better off that everyone's going to be. Another thing that sort of is a challenge at times, as with a sheet metal part, if you differentiate between the two, the sheet metal part has a consistent wall thickness all the way across. You can have a 6-inch part, a 6-inch wide front panel, you got 50 thousandths walls, not a problem. But if you notice here in this chart, what we're trying to show here is that as the overall size of the extrusion grows, so does the minimum wall thickness have to grow. So we can have some very small wall thicknesses, down around 1 millimeter or so if the part is smaller. But as the part grows in size, because of the extrusion process, it requires us to increase the wall thickness in order to get material flow through the extrusion die. So it's definitely a process constraint that we have here, which means if you want 50 thousandths walls across 6 inches, we're going to have a problem with that. And we're going to be working with you to try and get those numbers in this range here. Again, not set in stone, sort of a rule of thumb, but we're going to be looking at 80 thousandths, 90 thousandths, maybe even 100 thousandths in cases like that in order for the extrusion process to work properly. So good thing to keep in mind there too. Front panel pros and cons from an extruded standpoint. Again, sort of subjective, but the aesthetics, you know, you got the square corners and other features that can be built right into the profile itself. So that's a positive thing. And those extruded features are, we would consider all those things to be a pro, for instance, over the sheet metal technologies. Having the opportunity for differing wall thicknesses is good. And then the tooling costs are moderate. You know, you're certainly not looking at tens of thousands of dollars. You're looking at just maybe a few $1,000s for some tooling for an extrusion die. So reasonable costs as far as that's concerned. As far as some of the negative parts, well, the cost of those parts to manufacture as far as the cutouts, the I/O cutouts, connectors, those types of things, the machining process that has to happen in smaller volumes can somewhat be prohibitive to some. Higher volumes, we get into punching and stamping, so we can eliminate a lot of that. But most of the volumes are usually into the machining area. And then as far as the material options, well, you've got material. You've got one, aluminum. There's both different grades, so there are different alloys that can be chosen. But for the most part, you're only looking at aluminum. We don't offer this as a stainless steel extrusion, for instance, or a cold-rolled steel extrusion, nothing along those lines. The third one we'll look at is die casting. Die casting is a great process. We've been doing some of these over the years, whether it's a full front panel as you see on the screen here, or in some cases it might be just some ancillary fiber optic hood components that are attached to either an extruded or sheet metal component. But in this case, it's a great process. It really allows what we would consider a 3D design. So instead of being sort of linear in its process, you're able to have sort of features that are coming in from all different sides and angles, if you will. So it's a great process to use. And as far as the aesthetics are concerned, it's fantastic. Everything is needed. It eliminates an awful lot of machining, so your costs are incredibly low on a per-piece basis. But unfortunately, that does not hold true as far as the tooling is concerned. So as we look at the pros here, again, the aesthetics, the 3D contour design, your cost of the piece parts are very low, but your volumes have to be high usually in order to justify it. And the justifying has to happen with the tooling. So now you're looking at possibly tens of thousands of dollars for tools. The other problem that we've run into in the past with these die-cast parts is that usually there's a lot of inserting in the tooling that has to happen to allow for different configurations on the front panel, different I/O configurations on the front panel, where somebody might have an extruded or sheet metal part that can be very variable, all different types of cutouts, all different types of options and variability with that. With these dies, it requires inserts, which means more tooling, or it requires a whole other tool to create different variations of the same basic foundation part. So from that standpoint, usually it doesn't make sense, but there are some cases where the volumes are high enough where you have to justify it there. So again, nice process. We've done some of those in the past. Just some good things to keep in mind. It has its place, but not too many people, one of our customers are doing that. So as far as the front panel materials are concerned, this overall, we can't spend a lot of time with this, but basically what you're looking at here is that each one of these different processes have positives and have negatives. Some are all the way up to the 5 as far as the best, and then we have some number 1s down there as well. So it's all a matter of finding where you fit in here and which one of these processes and materials works for you, and then choosing the right one. And again, we can certainly assist you with that as well. We're now going to move on to our second key, which is the ejector. The ejector obviously is a very important part too of the entire system and how it all works. Very important, because nowadays, you know, there's just so much interconnectivity. Just pulling it out by use of a handle or something along those lines really is not going to work. So almost every single faceplate that we do, with the exception of a blank, has an ejector. So now we talk about what is the right ejector to use. Whether we want to use an internal style ejector, we'll talk about that. We'll also talk about an external style of ejector, and then we'll look at some of the materials and processes that the ejectors are manufactured from and see which one might be the best one. for the application. So starting off, we'll take a look at the internal. What do we mean by internal or external? Well, internal here, as you can see, the actual mechanism for insertion extraction sort of happens on the inside of the chassis. So whenever you have your mechanism working inside the actual chassis itself, that would be an internal ejector, which would require a slot, as you can see, and then the ejector goes beyond that attachment plane of the front panel to the chassis. And so your work is kind of happening inside. That's what we would consider an inside. A large majority, most of our ejectors that we do are the inside version because it's a pretty simple construction, although it does require a slot in the front panel, which sometimes can be an issue for EMI. When that's the case, that has driven a lot of our customers, or some, I should say, some of our customers to the external version. It basically means your attachment plane for your front panel to your chassis is inside, if you will, the ejection mechanism. This is probably the best one to see over here on the right-hand side. So you see the attachment plane, and then, of course, you see that mechanism sort of happening on the outside or the external part. This does require to have some sort of bracketing to hold the ejector to the outside of the panel. It's important to make sure that that bracket is mechanically stable to the front panel, whereas where you want to drive your force of the insertion extraction through that front panel. But that can be done in different ways. This particular version is a sheet metal part that is locked to the inside of the front panel to the printed circuit board. Another option would be something like this, where one of our customers actually designed the mounting bracket directly into an extruded part and then machined away the parts of the extrusion that would not be required. No opening, no seam. There's no opportunity for EMI leakage here. So it's really positive from that standpoint. Very structurally sound as well. And then, of course, the ejector mounting method can be a bunch of different ways. We'll talk a little bit about that too. And then this customer here had a little die cast block on the end, which then the plastic, in this case, ejector was just mounted to that with a roll pin, and that worked out well for them too. So a lot of different ways that this can be done. As far as the actual ejectors themselves, there are many different technologies that can be used. We see an awful lot of what we have right down here sort of in the middle lower, which is the aluminum extruded versions. A lot of different variations of those. Extruded out of aluminum and then cut to a certain size, and then usually finished with either powder coating or anodizing, iriditing, whatever the case might be there. A lot of those we do. Then, of course, there's just a straight-up stamped sheet metal components as well, which is certainly an option, a little bit more cost-effective, but a little less, as we would say, ergonomic. And then to really get into some ergonomics, again, we're talking now about the die-casted part, where a lot of different features can be added to that. Even overmolding in this particular case, which is a nice option. And then here we see another example of a different kind of ejector up in the upper left here that was a die-casted part as well. So a lot of different options that we have for that, and we'll talk about the reasons for some of those things next, which is like, for instance, down here, this bullet point insertion extraction forces that are required. Well, I think that's pretty much well displayed here. You have certain ejectors that are very long. So the amount of leverage required to extract that board from the chassis, because of the actual pound force that they have was so high, they had to have a nice long lever to be able to accomplish that goal. And then you can see it varies. And there are some others that are much smaller because there's not as much force required. So all of those things are options. This particular customer back here in this blue version actually had a little bit of a gear mechanism that was used to pull it out in stages. So a lot of different options there as far as those ejectors are concerned. One of the other things that ejectors can do is act as a hot swap feature as well, which we see here. Now this is just one example. It's actually an advanced TCA style, but here you see the example of hot swappability. This ejector not just inserts and extracts the whole board, but you see with this cutaway here, it does a couple of other things. The mechanism actually locks to the inside of the front panel to prevent accidental pullout, and then at the same time it actually triggers, in this case, just a standard lever style micro switch, which then turns the blade on once it's fully seated into the chassis itself. So just one example. There's a bunch of different ways that this is done, but we've seen a whole lot of those kinds of options. But it just, showing how else that can be accomplished. Here we see, just to finalize this general idea here, this general thought about the ejectors, is this balancing act that we have of trying to look at all these different considerations. How much front panel space do we have to play with has a bearing on the form of the ejector. the injection extraction force has a bearing on the length of the ejector, or maybe even the width of it, to make sure that it's ergonomic. How rigid the panel has to be, and making sure that you're driving the force directly through the actual printed circuit board, so it's having its maximum effect in insertion extraction. Whether it's an internal or an external, how you mount those to the front panels, and then of course we talk about ergonomics, making it look nice, the aesthetics, and then how it's hot swapped as well. So we've seen a lot of different ways to do this come and go. So we welcome you to talk with us about if you have any questions regarding that. As we move on to our third key, we're going to be taking a look at the EMI gaskets. So a few options here. I think many are familiar with, which is the metal finger stock or the fabric over foam. Those are the two main gasketing options that we have. Actually, a couple of more out there, but those are the two main ones that we're going to talk about. By far, we see these used more prevalently. The metal finger stock, when we talked about earlier about having an extruded feature, and that's worked out well for us, again, because we do a fair amount of extruded front panels, is to actually have that feature built right into the extrusion die. So there's no need for anything secondary. But you certainly can have these on sheet metal components. It just requires a part like this you see over here down here. So, I mean, you just snap on these rails to the side, and then the gasket will slide onto those snapped-on rails. So there's other ways that it can be handled as well, but just to show you a few of those options. And then as far as the material is concerned, primarily we're looking at stainless steel and beryllium copper with various finishes. Those are the primary materials that these shieldings are made from. And a lot of people like this. Doesn't require a lot of compression to be effective. It just simply requires a contact and making sure that you have those contacting properly. With fabric over foam, it's a little bit different, because with fabric over foam, the actual shielding effectiveness has to do with the compression. And this chart in the lower left shows that. See the compression going higher, and then your shielding effectiveness or your resistance actually growing along with that. So it's important to make sure that in a case like this, you're retaining that gasket properly inside some sort of a feature. That's why we recommend extrusions, maybe in a case like this. And then obviously making sure that you're maintaining that gap that we did talk a little bit earlier about between each one of those front panels, to make sure that you're having the right amount of compression without being overly compressed so that it becomes difficult to insert and extract, but of course not being under compressed so you lose EMI effectivity as well. So things to keep in mind for that. And some of the things that help us right along those lines would be the fasteners that are chosen. For instance, how can alignment pins be used to help that EMI gap? We'll talk a little bit about that. We'll also talk about panel fasteners to hold the front panels to the chassis themselves, and then some ways that the printed circuit boards are mounted too. As we look at the alignment pins, I think it's pretty self-explanatory. An alignment pin just basically holds each one of those blades sort of in their home, within their pitch. If you don't do that, the compression that you have with either a metal or fabric over foam gasket can cause the whole sort of front panel system to move. If you've got a blade that's empty over to the left-hand side or right-hand side, and you're trying to fit it in there, and you don't have these things being held in place, well, that compression can start to really compact that open space. So therefore, having an alignment pin to keep each one of those front panels locked in their spot and keep that gap between the front panels more as a set distance will certainly be effective when you come to shielding. We recommend alignment pins for these kinds of applications. As far as panel fasteners, there again, so many different options. We've done a whole bunch. It all depends. Some are they like colors, they want plastic. Some need metal. Some have tool access only. So therefore, they have to be either hidden. They can't be thumb screws. They can't have knurls on them. And then others don't have quite that kind of restrictions. So therefore, we work with whatever you want, whether they're flare-in style, because sometimes these things are actually used to extract boards that pull on them. You might want something a little bit more robust than a press-in style. Either way, we have a lot of experience with working with all different types of these fasteners. And then finally, in this section here, we have the printed circuit board mounting. More commonly, I think you see what you have right here, just a standard pen that's pressed into the side, that's threaded, and the printed circuit board gets attached and screwed directly to that. And then you see in this case it actually is integral to the ejection mechanism itself, which is nice. So everything's kind of tied together in one central pivot point, central location, structurally sound, rigid, and simple, cost effective as well. Other ways that it can be done are with custom types of PEMs, as we see in these few examples. And then finally, really not cost-effective at all, but very rigid is a situation we actually extrude, again, a feature right into the extrusion die, an integral component to the front panel, and then simply machining, eliminating the excess material away. So it's the machining process that kind of gets you from a financial standpoint, but as far as mechanically, it's a very sound way to go. As we wrap up our fifth key, we're going to talk a little bit about finishing here, and couple of options that we have: the silk screening, overlays, and then different metal finishes that we offer as well. As far as silk screening is concerned, I think it's been around for an awful long time. Many of us are very familiar with it, just drawing ink down. Usually you're looking at just a couple of colors. You see down here, 1 or 2 colors of silk screen is pretty much what you're going to be looking at. And then the only recommendation there is that whatever finish, the substrate on the panel itself that you use, just making sure that that's smooth. You don't want to have silk screening on a textured powder coat as an example, because the silk screen has a tendency to bleed, and therefore you'd lose your resolution on the screen itself. Overlays. By far, I think most of the work that we do is overlays, and the reason I think might be pretty evident here on this slide. You can have an awful lot of different kinds of colors, logos, nomenclature. Things stand out, very well. Another feature is, having clear windows to sort of hide the LEDs and diffuse LED light, which is an important thing for a lot of people too. And even some have even included membrane switches directly onto the front panel, so they're actually active. You can actually do things directly on the front panel with some membrane switches and have an effect on what's going on for the electronics of the board too. Cost-effective way to go, yet also very aesthetic way to go as well. And as far as the actual finishes of the front panel, many different things that we do from a conductive standpoint. Mostly it's clear chromate or a trivalent chromate finish, which is a chemical film, protects the aluminum from oxidization if you're using aluminum. If it's a sheet metal, it's a zinc chromate finish. If it's die cast, it can be usually some sort of an electroless or electrolytic nickel finish as well. The nickel can be accomplished on all the different modalities that we talked about too. And so it's pretty much what you're looking for, what you want. There's various reasons for each one of those finishes. It's just a matter of finding out either what your intent is, what you're looking for. Your cost point also has a bearing on this as well. So there's just considerations, but we have the opportunity to supply all of those. And even in-house here at our factory, we have our own in-house powder coating as well. So we can offer a lot of different options as far as powder coating, if that was the way that one wanted to go. Mostly we see the powder coating on the ejectors. Front panels occasionally are masked and powder coated, but normally they're covered with something else like an overlay. So in summary, all the years of experience that we have here, we're proud of. We've had the opportunity to see all different, ways that every one of these particular things that we talked about have been handled, have been managed. Sometimes it's a blend of them, And so we have the opportunity to share that experience with you. So that's what we ask, the opportunity to let us put that experience that we have to work for you with any questions or anything that you have, or will help with your design. And we want to be able to do that. So with that, I say thank you very much for attending. We appreciate your time with us today. Hopefully you were able to gain something from it. But if not, feel free to contact us if you'd like a copy of this presentation, or if you have additional questions. Here on the screen you can see some emails. Feel free to send an email and somebody will get back to you right away. So again, thank you very much. Have a good day.